All right, class, I had to take a quick little break here. So now we're moving on with number 49. Number 49 is still the same directions here. We're going to go from 0 to 360. We're just shy of 360. And we're going to be rounding off answers to the nearest tenth of a degree. In fact, I think I'll just show you just a quick little method for this one since it actually has 4 theta in here. Oof, okay. 4 theta. All right. Yeah, that would be good to show a quick little method here to do that. Okay, let's start off right here. So first things first, I look for my linear form. Linear form is sine, and that is not sine right here. So I'm going to have to change using Pythagorean theorem. Change sine squared as cosine squared into sine squared, and we do it by this right here. So notice also that it's still a 4 theta here. It is squared. So cosine squared theta is the same thing as 1 minus sine squared theta by Pythagorean theorem. Perfect. So that's the case. I have this, and I get to distribute that 4 in there. Just a second here. All right, and then keep on going here. Let's see, I got this, there. And then let's put our sine squared in front. And then our sine here. Let's move this out to the front. There'll be a +2. And I notice I am going to have to factor. So there I'm already thinking ahead. I'm going to have to set it equal to 0 here. So I'm going to subtract 1 from both sides here. So I got negative 2 sine squared 4 theta. And the rest. And then before I start factoring, possibly doing quadratic formula, I don't like to have my negative term to be my leading term, or my leading term to be a negative term. That's probably better to say it. So I'm going to multiply everything through by -1 on both sides. And if that's the case, I got myself 2 sine squared of 4 theta. I'm going to just switch the signs here. So that's minus now. So minus. Okay, cool. So now I am possibly factoring, possibly using quadratic formula. So just to check, just so it looks a little bit easier in my mind here, I'm going to just check this. Is this possible to do if I go back to my algebra 2 ways? I just want to see if that's possible, because if that's possible, then I have my sine squared 4 theta is the same thing. And so the only way to get a 2x squared is 2x times x. Oh, going a little too fast here. And the only way to get a -1 is a -1 times a +1. But if I do that, -1 times a +1, notice that gets me a -2x. That gets me a +x. And the only I can do is get a -x here. I can't get a -2x. So that does not work. I'm going to have to use quadratic formula. So QF, quadratic formula, here we go. So sine of 4 theta is equal to, all right, let's go with this one here. So that is my A value. That is my B value, and that is my C value for the quadratic formula. So my quadratic formula, if you look it up if you need to here, but it's negative of my B or opposite my B value plus or minus squaring of my B value, then it's 4 times A value times C value all over 2 times A value. Okay. And so I got myself 2 plus or minus, that makes 8 minus 8. So subtracting a -8 or a -8 makes a +8. So that's 12 over 4. And that was really big. Bar line over there. Let me make like this. And then I got myself 2 plus or minus, let's see, 12 is 4 times 3. Perfect square of 2 goes out, left over of a 3 all over 4. And I'm going to have to reduce this. I can reduce it if and only if I can find a number that goes into 2, 2, and 4. And 2 would do it. Keep the same color here. Divide by 2, divide by 2, divide by 2. And now we are ready to look at sine of 4 theta is equal to 1 plus or minus root 3 over 2. That's what I'm looking for. So, okay. So those are two different answers. Gonna have to go to the next slide. So I have two things happening here. I got a sine of 4, write 4 like this, just to change it up. 1 plus root 3 divided by 2, and sine of 4 theta equal to 1 minus root 3 divided by 2. And let's test this guy right here. If this is above 1, it doesn't work, or below 1 doesn't work. So let me get to my calculator here. So I got myself, let's see, 1 plus the square root of 3. I'm going to press enter right there. Divide that by 2. Oh, it's above 1. Perfect. I don't need to deal with this one here. So this is the only one that's going to give me some answers here. So let's go with it here. So this is going to be 1 minus the square root of 3, all that, and divided by 2. Okay, perfect. Oh, also notice it's a negative. Okay, so here's what we got. I'm going to have to do this by calculator. Oh, I'm going to show you a quick little trick here as well. This will find easier to do here. Okay, it's negative. In order to get the reference angle, my reference angle always has to be positive. So here's what we're going to do. We're going to take this, and I'm going to use the reference angle here. And the reference angle is the positive whatever this is. So the approximately 0.366025. So approximately 0.366025. That's what I'm using. But if I do it on the calculator, trying to get as close as I can, what I want to do is I would just multiply this by -1. So how about multiply through by -1? That changes that into a positive. And then I'm going to just take the sine inverse of my answer. So in order to get answer, you click the second function and you click the negative symbol here because it says answer right there. And I have that does not sound right. But yeah, maybe it is. Let's see, 21.47. And if we want to get to the exact answer, we can kind of keep a few more extra decimal places here, not like we did last time. And if you're off by a tenth, that's fine. But I'm going to go with 21.4707 as my reference angle. 21 points. So when I divide by 4, I will still have a good approximation to the 10th place. Okay, so reference angle is 21 point, and since we have calculators, it's pretty easy to do. Okay, my 7s, I usually go like this with my 7s. Pull dash on them. That's my reference angle. That is theta hat. I'm looking for negative values because this right here was actually negative. So I'm looking in quadrants 3 and 4. In fact, just like we did on the last problem. Okay, I'm looking for these ones. Okay, the relationship between theta here, the angle here, and the reference angle is 180 plus theta hat. The relationship here is 360 minus theta hat. Okay, let's plug it in here. So with calculus, it's pretty easy to do. I'm going to take that number plus 180. So 201.4707. Okay, 201.4707. On this one here, I'm going to have to type it in now. So it's 360 minus 21.4707. 338.52. So let me do this here. So 338. 5293, 5293 with some degree symbols there. Okay, so that, again, is not equal to theta, right? Theta is just my angle that I just found in quadrant 3 and 4. What I'm really looking for is 4 theta. You know what? Let me just change the color on this one as well here. It's just easier to see there. So let me go with it. 201. Okay, and let me move this so I can get both answers on here. There's that one, and there is this one. It's 338.5. Oh, the degree symbol goes at the end here. So let me put some degree symbols here. There's that one. There's that one. 5.2. I think it was 9.3 here. Yep. 9.3 degrees plus 360. Okay. Okay, at this point, after we divide by 4, then we're going to reduce it down to the nearest tenth. So let's divide this guy by 4, this by 4, and this by 4. And that's going to give us our theta terms. So let's go back to calculator. So 201.4707 divide by 4. 50.4. Okay, so that would be 50.4 degrees plus 90K. Perfect. Okay, over here, we'll go with divide by 4, divide all that by 4, and 4. All right. And we go with, we'll go over here again. So 338.5293 divide by 4, nearest tenth would be 84.6. So 84.6 degrees plus 90K. Okay, so here's a little trick. We know we're going to have to do 4 revolutions, true? So no, we're going to have to use K values of 0, 1, 2, and 3. So here's a little fast way to do it. Let me put some degree symbol right there. So on your calculator, you're just going to punch in 50.4 plus 90, right? So you know 50.4 is already an answer, right? 50.4, that's already an answer. So the next one is 50.4 plus 90. Click enter. That's 140.4. And then what we do is you just press plus 90 again, right? Because technically this is k is equal to 0. This is k is equal to 1. Once I click run it right now, that'll be k is equal to 2. And then plus 90 again, that'll be k is equal to 3. So I have all my answers right here. 50.4, 140.4, 230.4, and 320.4. Perfect. Got all of them. That was a lot easier. All right, let's do the same thing over here on this side. So it'll be 86 point. So you know that 84.6 is already an answer. We just need the other 3. So let's do it like this. In fact, let's clear the calculator out so we can kind of see it. So 84.6 plus 90. So that's k is equal to 0. Once I add the 90, that's k is equal to 1. Plus 90 more, that's going to be k is equal to 2. Plus 90 more, that's going to be k is equal to 3. Perfect. I got all my answers right there. And let's keep on going. So 84.6, comma, 174.6. Yep. 264.6 and 354.6. There it is. So that's all the answers right there. And got it. Okay, so that is the canon problems here. Shifting now to the honor questions. I got 51, 53, I believe, and 55. Okay, 51. It says in example 6 in section all the way back in 4.5, when we were talking about the Ferris wheel, we found the equation of the height of the Ferris wheel, the passengers on the Ferris wheel, to be that. Use the equation to find out when passengers will be exactly 100 feet above the ground and round your answers to the nearest tenth of the minute. Use your graphing calculator to graph the function and verify the answers. Okay, so let's go with it here. So here's my little formula. My formula is h is equal to 139 minus 123 cosine of pi over 10 t. Okay, so we want to know, when are the passengers going to be exactly 100 feet above the ground? All right. Okay, so let's talk about this just for a little bit. Okay, so we have a Ferris wheel like this. There's the center. And we have a Ferris wheel like this, and little spikes, or this little, what are these called again? I forgot, spindles or spokes. There you go, spokes. They go like this here. So I got a passenger here. So when are the people going to be 100 feet above the ground? So this has a radius of 125, because that's, oh, sorry, I misread that here. 1 second, let me change up a little something here. That should be 5 instead of 23. There it is. So I believe this said, if you go back to section example 6 in 4.5, I'm going to go to it real quickly here, just to give you a little context for it. All right, that means we have a Ferris wheel that's going up and down, and it is, this guy here, it's already 139 feet up in the air, right? So the middle of a Ferris wheel is 139 feet up in the air. And then what happens? It goes up 125 feet higher, and then also goes down 125 feet higher. And the reason for it is because the platform which is standing on, right here, that little piece is 14 feet high up in order for the people to go up the stairs and then get into the cars. Okay, so if I'm talking about 100 feet, that means I'm really talking about something looks like right here, right? Somewhere like right there. That's what I'm looking for. Oh, and I noticed there's like 2 exit points here too. That's interesting. Okay, so let's see what happens there. Let's go with it. Just to give you context here. So I'm going to subtract 139 from 100, leaves me negative 39. Negative 125. Cosine of that. Okay. Let's see, I'm going to divide everything through by negative 125. Negative 125. All right, and I need my calculator for that. So it's 39 divided by 125. Okay, that's nice. That's a nice answer. 0.312. 0.312 is equal to cosine of pi over 10t. Okay, let me just do this real quick here. Let me just move it around. I like my trig values to be on the left-hand side and what I'm solving for to be on that side. Okay. So let's see what I got here. So first things first, it's not degree measure, it's radian measurement. So I'm trying to find when this takes place. All right, let me just write it over on the next slide here. Maybe just easier to think through here. Okay, so I'm looking for cosine to be 0.312. So that happens 2 different spots. That's interesting. It happens here, right? Quadrant 1 and quadrant 4. So what I'm going to do is I'm going to use my calculator. Let's go to radian mode now first. Okay, and then we're going to take cosine, because it's positive already, so cosine inverse of 0.123, or 3.312. And we get an answer of 1.52. Let's go with, let's see, 1.2535. That'd be good. 1.2535. That's pretty close. That'll give us at least some kind of direction. So that's that angle. We already have that. So reference angle in quadrant 1 and the angle itself are both the same. In quadrant 4, it's 360, or 2 pi in this case, right? 2 pi minus 1.2535. So let's go 2 pi minus 1 point, actually, no, just minus our answer, would be even better. There it is. So 5.0297. 5.0297. Okay, so let's go with here. So this is that t value, because we're just doing one revolution, is that right? 0.312. Oh, sorry, 1 second there. Got rid of that already. This is 1.25350 plus, remember, 2 pi k, right? Because it revolves and keeps on revolving. And this would be that is equal to 5.0297 plus 2 pi k. All right, so we're going to multiply everything here by 10. Let's see if this makes sense. We're going to multiply everything here by 10 and here by 10. And then we're going to divide everything by pi and over here by pi. So that'll be interesting. So we might have to do this a little bit at a time here. So t, let's do this here. Let's multiply everything by 10 first. All right, this would be 12.535 plus 20 pi k. And now let's divide everything through by pi. So I just multiplied by 10, divide by pi now. Oh, interesting. Look at that. T is equal to, and we'll have to do that on the calculator here. It is 12.535 divided by pi. The little pi button right there. 3.99. So now we can round off to the nearest tenth. So 4.0. So this is 4.0 plus, those pi's are gone. What's up with the 20? What is that all about? All right, it's the 20th because if you go back to 4.5, it says it takes 20 minutes for the Ferris wheel to make one full revolution. So there's your 20 for that revolution. Okay, let's do the same thing here. And we're only talking about one revolution, is that right? So what we do here is we just say, oh, let's finish off this one here. So since we're only talking one revolution, we're going to plug in that. So at 4 seconds after it starts, 4 minutes. 4 minutes after it starts, let's go back over here just so we make sure it makes sense of it. So there it is. 4 seconds after it starts here, the passengers are here. 4 minutes, sorry, 4 minutes, that's right. 4 minutes later, they'll be right here and they'll be exactly at 100 feet high in the air. Okay, so now let's go to the next one. We're going to multiply this by 10 and this by 10. And we get ourselves pi t is equal to 50.297 plus 20 pi k. And then we divide by pi. Divided by pi, divide by pi, divide by pi, and the pi cancels here too because of the 20 minute to make one full revolution. And we get ourselves t. T is equal to, and then let's do that. What is that going to be? 50.297 divided by the pi value. Pi, enter, and it gets me, oh, nice, 16.01, roughly 16. So 16.1 plus 20k. And I think I know what's happening here as well, because when k is equal to 0, that just means 16 minutes. So what's happening with our Ferris wheel? And now it should kind of make total sense now. Like, oh yeah. So when the passengers are here, 4 minutes later, they reach 100 feet up in the air. And then they travel a long way. They travel a full rotation of 16 minutes. And they hit again another 100 feet in the air. And if they go another 4 minutes, they'll actually make one revolution. So, but the answers are here and here. The answers are, there it is. Time is 4.0 minutes and 16.0 minutes are the 2 times during the cycle that they are going to hit the 100-foot mark above the ground. Okay. All right, so let's go to number 53. So it's a little bit of a geometry question here. So maybe in geometry class you guys study this. So just as an example here, I have a hexagon, almost supposed to be a regular hexagon. And here's a relationship. If I mark something right in the center, and this is R, that's theta inside here, and this is L, called the lateral side. There is a relationship, in fact, a trigonometric relationship that says this, that the lateral side is equal to twice the radius multiplied by sine of 180 over n. And that's the relationship between any lateral side, if you know the inside degrees. So any regular polygon. Okay, it says this. It says if the radius and the lateral side were both exactly the same, question is, what would be the n value? And so, let's see what that is. So question, yeah, so let's go with it here. So we're going to plug in, if R and L are both the same, in fact, it says substitute L for R. So we're going to do this right here. So that is the case. If the radius, I can put parentheses around here if I like, that's fine too, like that. So if L is equal to R, lateral side is the same as the radius, then the question is, what n values, how many side lengths can there be for this to happen? All right, so let's go with R. Oh, we can divide all this by 2R, this by 2R, and notice that's going to go away. That gives me a 1/2 is equal to sine. That looks not so nice. There. Okay, there it is. Sine of 180 degrees over n. Okay. So I have to find. So let's see what it's saying is, are there, yeah, let's go back to it here. So geometrically speaking here, what sides would give me a lateral side right here, which is the exact same length as my radius? Does it happen all the time? Is there only specific ones that would do that or not? That's the question. Like if we take, okay, let's do this here. If we take like a equilateral triangle, right? Like this right here, right? Oof. And if I go from the middle, there it is, right? My radius is going to stick out to the end right here. So notice that radius and that lateral side are not the same. That can't be, right? So let's go with this. If it's a square, if square is my geometric figure, and I have that dot, and I go here, is it possible that the radius will equal lateral side? Not possible. So for n is equal to 3, does not work. For n is equal to 4, that does not work. So the question is there a polygon? Is there a polygon in which the radius and the lateral side will be equal to each other? That's the question. And so let's find out. So we say, make the lateral side equal to the radius and solve. So the question is, when does sine give you 1/2? Well, let's see, sine gives you 1/2 at 30 degrees, and then also at 150. Cool, okay, so let's do that here. So let's see. So that's going to give me 180 and is equal to 30 degrees, or 180 divided by n is equal to 150 degrees. So if that's the case, multiply both sides by n. I got myself 180 is equal to 30n. Divide by 30, divide by 30, and we got n is equal to 6. Okay, that's perfect. So this happens, this can only happen if, what the figure that was, 1, 2, 3, 4, 5, 6. This can only happen if you have a hexagon. The R and the L actually equal to each other. And then the other one, let's see what this happens. You multiply both by that. And we get ourselves this, divide by 150, and that is not going to happen. This turns out to be n is equal to 1.2, I believe. Let's check. So turn on, got 180, divide by 150. Okay, 1.2. So, and that is not, we can't have 0.1 of an n-gon, right? So that does not happen. So the only time this could ever happen where the radius and the lateral side are equal to each other is when you have a hexagon, or when n is equal to 6. So a polygon of a 6-sided polygon is the only time that can happen. Okay, moving on to the last problem here. We got ourselves the rotating light problem. So let's see if this makes sense here. I'm going to draw. True, this thing has, sorry, excuse me. This thing has, it's a ladder truck. That, put a little fire truck like this, traveling down the highway. Okay. And we have a wall that's right here next to the highway. And we have the rotating of the light right over here. This light is rotating, and what happens is it sends out light. It sends out light to here, then it sends out light to here, and then to here, and then to here, right? It says we found the equation. So this goes from example 4 in section 3.5. It says as the distance of the light increases, right? We found out the distance of the light. So from here to here, that'd be the distance of the light, increases as it rotates. Notice D is getting larger and larger and larger. And the funny thing is, when it becomes exactly parallel to the wall, it's infinite, right? So what trig function models that equation? It's this one. So D is equal to 10 tangent of pi t. I'm sorry, it took a little bit of time to look at that problem again here. Sorry, it is not, D is not the length of the light. D is the length right here from D. D is this length right here along the wall. So here's that. And it tells you how many seconds it gets to there. So if this right here is 0, right? As the distance increases, it takes maybe like 0.2 seconds to get to here. It may take a half a second to get to here, right? And eventually it goes off to infinity. And so as soon as seconds go by, there's a point at which D is infinity, and then it comes back around. So it's this distance right here from the starting point to the ending point. Okay, now let's look at our problem. If a person is standing against the wall 10 feet from the point A, so this is point A right here, and then we got Stickman right here. Stickman just chilling along the wall. And he's exactly 10 feet away from point A. How long after the light is a point A will reach the person? Okay, so then how long is this going to take to get there? That's what we want to do. Okay, simple enough. I think the understanding of the problem is the important part, just kind of honing in what does that even mean. So it does give you a hint. It just says put in 10 for D. And then at that point, we should be okay. So divide by 10, divide by 10. We're trying to figure out when is tangent equal to 1. All right, so tangent is equal to 1 right here, right at pi over 4. And then also at, right here at, so pi over 4. right? And then next at 5 pi over 4. But we don't need to make two different equations out of it. Remember, the easiest thing is to make one equation out of this. What we do is we just say pi over 4 plus, instead of putting 2 pi k, we just put pi k, because that takes care of a half rotation each time. Okay, to solve for t, what we got to do, we have to divide everything by pi. So divide by pi here, which is the same thing as multiplying by 1 over pi and dividing by pi. So if we do that, notice what's going to happen is t is going to be equal to, pi's are gone, this is 1/4 or 0.25 plus k. There's our equation. All right, so what is it going to do? Well, it says this, from the time that it starts here, so this is our initial point, it's going to take exactly half or quarter of a second to hit the guy, the light to hit our stick man that's against the wall. And then it's going to take 1 second to go all the way around, and it's going to hit him again at 1.25 seconds. And then as the light swings back around, it's going to hit him again at another 2.25 seconds. And again. So it's hits him at a quarter of a second rotation from the wall, and then here on out afterwards here. So how do we write that? So T is, so after 1/4 of a second, and let me rewrite it here. So 0.52 seconds after the light goes through point A, right? And every second after that. Okay, that's one way to do it. Okay, another way you can probably write the answer is t is equal to 0.25, comma, 1.25, comma, 2.25, comma, 3.25, right? You can start listing them like this to get the pattern going, and then you can say ... That's another way. That's actually would be a correct way of saying it as well. All right. Hopefully that was good, and we finished up all the homework at this point.